now we've seen how to use the semantics to prove correctness. Now that we've done that, let's take a closer look at the actual semantics itself. Now the semantics consists of two steps. So the first step is to translate the program into the kernel language. A simple language, it has all the essential concepts of the paradigm. And all programs in the practical language can be translated into kernel language. The second step is to execute the program in kernel language on the abstract machine. And the abstract machine is a simplified computer with a precise mathematical definition. Now let's take a look more in detail. So here is the actual kernel language. In fact, we have seen the full kernel language of the functional paradigm with all the instructions. So these are the instructions in there: skip, sequential composition, local, binding to identifiers, identifier value, if, procedure call, case. We've seen the different values, numbers, procedures, and records. Those are all the instructions, all the types in the kernel language of the functional paradigm. So we've seen that. Now let's take a closer look at the abstract machine, which we haven't seen really in detail yet. The abstract machine consists of the following concepts. In fact, we've seen already some of these concepts. The abstract machine has a single assignment memory. So sigma here, which contains variables that might be bound or maybe that are not bound. X2 is not bound, X1 is bound to 10. And it also consists of an environment, the concept of environment with the link between identifiers and variables in memory. So we've seen that part already. But in fact, there's more. In fact, there are the instructions. Remember here, S here is an instruction in the kernel language. But this instruction by itself is not enough to execute. We have to make a link between the instruction and the memory. And this link is given by the environment. So that's what we call a semantic instruction, is an instruction together with its environment so that it actually knows what variables it's working on. And in fact, in the execution, we need more than just one instruction. We will need a stack of these instructions, because maybe you do something and then there's instructions that are kept for later execution, and these have to be kept somewhere, so you need a semantic stack. So that is the second part of the abstract machine, which are the instructions. The third part here is the actual execution. And this consists first of an execution state. At any moment in time, we have a semantic stack and a memory. So the instructions that have to be executed and the memory that they work on. And then the actual execution is a sequence of these states. We start with an initial state, an initial stack, semantic stack, an initial memory. And then we do one execution step here, this arrow, and that gives us a next execution state, which is a stack and a memory, and so on. So you have a sequence of execution states, which goes on, and it keeps going on until the stack is empty. So that's the third part of the abstract machine. So these three parts together form the abstract machine. And when we execute a kernel language program, we have an execution algorithm, which is basically a loop. So we start with an initial semantic stack, which has an empty environment together with the instruction we want to execute, and an initial memory also, which is empty. So there's no variables and no links between identifiers to variables. That's how we start. And then we have an infinite loop here, or a loop that keeps going until the stack is empty. So while the stack is not empty, we pop off of the semantic stack a semantic instruction, which is removed from the semantic stack. So the semantic stack will have one less element. And then we execute this instruction according to its semantic rule. So each instruction in the kernel language has one rule, and here it takes an execution state, the semantic instruction, and it returns the next execution state. And then the loop continues, and it keeps going until the semantic stack is empty. So we now still have to define these rules. So the rules that define the execution of the instructions in the kernel language, we need those, and then we will have the complete abstract machine. There is a small remark here Later in the course, when we introduce concurrent execution, we will generalize this machine slightly. We will allow more than one semantic stack, because each semantic stack will correspond to a thread. But for now, we have programs that are sequential, and we have one loop that executes all the instructions in the kernel language program.